Okay, so I'd like to thank the organizers for inviting me to speak here. I'm going to probably come from a different angle from a lot of people here because excuse me. I'm going to be talking about a software solution to the general computing problem that we're all facing now. Okay, so we've heard the talks this morning have all reminded us that Moore's law is running out. We're hitting the limits of what we can put on chips, and the problem size is growing at an exponential rate. We want to do inference, eventually over tera and petabyte databases, and so if we want to keep pace with those kinds of problems, we have to come up with computing technology that scales exponentially as well. And so we have two places we can look for that, hardware and software. So a lot of the esoteric, or I guess they're not esoteric because they're all being developed now, hardware technologies will probably bring several orders of magnitude of improvement. But I will argue that, or I'll tell a story that I think the greatest gains we can make in computing power will result actually from a software change, and in particularly from changing the data representation from localist codes to sparse distributed localist representations to sparse distributed representations. So currently, virtually all data in the world that's used anywhere is represented using localist codes. I'll explain the difference between the two representations in a moment. But every database, Oracle database everywhere on Earth stores individual records in individual locations in memory. That's a localist code. So the reasons for an SDR is the shorthand I'll use for sparse distributed representations throughout the talk. So the reasons for SDR's increased power, one reason is that you can represent a lot more than M items or hypotheses in M units. And the reason I'll introduce more here today and focus on is that SDR allows you to evaluate the likelihoods of all stored hypotheses in your SDR memory with a single pass over the computing elements. So in the case of a neural network, which my model basically is, a single pass over the weights or the units comprising the system evaluates all of the hypotheses stored in the system at the same time. You don't have to iterate in any sense over the actual items that are stored. So this means that SDR admits a constant time algorithm for computing the maximum likelihood hypothesis, or in other words, for finding the closest matching item in memory. And since that inference algorithm is the core part of what's done during learning, when the model stores new information into memory, it also admits constant time storage. So we all know probably in here that about hashing functions have constant time complexity on both sides, storage and retrieval, but they don't do nearest neighbor retrieval, and there's a lot of research efforts underway right now to try to bring that. So the algorithm that I'll describe today has those properties. So that's a picture of a localist code, M units, and every item is represented by an individual unit. The representations are disjoint, and that can only represent M items. So this is one picture of SDR. This is the kind you see in Canerva's work, for instance. And here, every item is represented by a subset of, in this case, binary units chosen from a field of M units. Here's another flavor of SDR, the kind I use in my work, where I break that field of M units up into a number of winner-take-all groups. And my codes just choose one item, one unit from each of the groups, and that's the code for an item. So the code spaces for either of these SDR implementations are exponentially large. I mean, MCQ for the Canerva-like version and K to the Q for mine. That doesn't mean you're going to be able to store K to the Q hypotheses in an actual practical working memory, because there are other constraints that will come into play, but it's a lot. It's much larger than M. So a key advantage of SDR is that you can represent, since items are now represented by a group of cells, you can represent similarity between items by the size of the intersection of their codes, and so you can't do that with localist codes. So if we can define the activation strength of an SDR code as the fraction of its units that are active, then if I turn the code for A up in the right-hand corner there on, that I simultaneously partially turn on the codes for the other three things represented in this memory. So they're physically all active in proportion to their overlap with A. If the algorithm that you use to assign codes to input items preserves similarity in the input space, then that statement becomes that if hypothesis A is maximally active in the memory, then all the other hypotheses are simultaneously active in descending proportion to their likelihood or similarity or relevance, whatever measure you want to use. And again, you can't do this with localist codes. If you turn one unit on in a localist code, you haven't turned any other items on. If you want to, you've got to do additional computing steps to do that. So there's no additional computational cycles needed to light up the whole probability representation with SDR. I just want to clarify two senses of sparse representations that are in the literature. By far, the more prevalent one is the idea of a sparse basis, from Olshausen and Field's work and many others, which is just that the number of features needed to represent an input space is small compared to the number of all possible inputs you could see in that space. Vanishingly small fraction. So most of us have seen pictures like this. This is from a paper from Lee and Gross et al. Showing a four-level model, and these are the bases learned at each of four levels, progressing up a featural hierarchy. And the key point I want to make here is that in all papers that I've seen that are talking about this, they're using localist codes to represent each feature. So each of those little edge features is represented by a single unit somewhere, and that's true all the way up their hierarchies. And again, that contrasts to what I'm saying with SDR, which is that every feature, or if you want to call it a concept or an item or a hypothesis, everything is represented by a set of units, even the lowest level units. So here's a picture of a sparse coding field that I'll use in the rest of the talk, where the field consists of, in this case, 7 winner-take-all clusters, and each of those clusters consists of some number of binary units, representational units. And so that might be the code for that particular feature, as opposed to just a single unit. And the feature below it, which is maybe kind of similar to it, might share a lot of its units in common. So it has the dashed lines show intersecting units, so it has, I think, 4 out of 7 units in common, as opposed to this less similar feature, which only has 2 units in common. Okay, so this is a visual hierarchy visual feature hierarchy proceeding from low level to high level. Edges down at the bottom, progressively more complex features, and then high level abstract concepts at the top, and adapted from one of Thomas Sayre's papers. But it's really indicative of, I believe, all the HMAX models, at least the ones I'm aware of, and Neocognitron, a large class of models that are developing visual feature hierarchies. But what I want to emphasize here is that this uses a localist code for features at all levels of the hierarchy. Down at the bottom there, that's just a picture of a dog's head on an input surface, and each of those little gray hexagons is an aperture of visual space that's seen by a patch of cortex. That red rectangle, the red rectangle is over there. Now, this is what a visual hierarchy looks like or can look like when you generalize from localist codes everywhere to sparse distributed codes everywhere. So there's a lot. So the two pictures are analogous. On the right-hand side, you can see that the vertical feature and the horizontal feature in those two visual apertures are represented by sparse codes, and they feed up into a next higher level of cortex, where a combined feature, a feature that's a composition of those two, is represented by a sparse code. And the call-outs just show that there's a large number of codes that could be stored in any of these apertures, any of these Okay, I'm going to call these macro columns because my hypothesis is that the sparse distributed module is a macro column, is a cortical macro column. And so what I'm showing here is that all the way up the hierarchy, everything is represented in the same way. And so to emphasize the advantage again over SDR is that on the right-hand side, when the vertical and horizontal bars are present, the speed with which that corner feature is activated is in constant time. It's immediately activated. There's no search over the features stored. in that macro column at the C1 level. And that just shows that well, there are top-down, bottom-up, and horizontal projections throughout the model. The horizontal projections carry information from one time step to the next. So the blue arrow suggests that. This is the domain I'm working on now in my projects. I'm working on an ONR project right now and soon a DARPA, and they're both about understanding video, events in video. My model is binary, and so I take, these are Hollywood 2 video, database video snippets that I edge filter and then binarize, and of course we can all tell what's going on here. And this is a picture of the first two levels of an instance of my model. So you can the larger pixels are level 1, the input level, and then superimposed on that is a grid of macro columns. You can't really see the detail here, but this zooms in over here. The idea is that the macro columns are the blue squares, and whenever there's sufficient features, feeding up bottom up from the input, they become active. And this was not a tuned model or anything, so you'll see a lot of contours that don't get lit up with macro columns, but the idea is there. And on the right-hand side, each macro column, you can see that each macro column consists of, these are 5 by 5 mini columns, or those winner-take-all clusters, and the little black dots are the individual units being chosen. Oh, I'm sorry, are the individual units being chosen. When the feature sweep, I think you got that probably. There'll be more videos. So this is the algorithm that I'm going to describe now. It's only got 8 steps to it. So the first step, so I'm showing one macro column here, and I pulled out on the side there is one mini column consisting of some units. It's got top-down, horizontal, and bottom-up inputs. And the first step of the algorithm is just to sum your weighted inputs, like occurs in most neural algorithms. The next step is to normalize those input summations to 0, 1. And so there's some complexities to normalization, which we can go in questions or later. But basically, you can normalize those inputs to 0, 1 measures. And then the third step in this case is to simply multiply them together to get what I'm calling a local degree of support or evidence that a unit should become active. And I'm going to call that V. Now, in the next few slides where I describe the rest of the algorithm, I'm only going to use the spatial case. So I won't be needing the horizontal or the top-down inputs. And so in that case, the capital U is capital V. So I'm just giving you that notational heads up. So this is a picture of a macro column with, in this case, 6 mini columns. And so after those, so no multiplication of U, H, and D is necessary in this example. Rather, U just passes straight through to V. So the third step of the algorithm is you just compute the max V in each of these many columns, and this is a hard max. It's the first of 2 rounds of competition in the algorithm, and those are all brought down to the box down there, and I compute the average of those maxes, and I say the model computes them. If my brain works like this, then I guess I'm doing it too. And G is a measure of the overall familiarity of the input to the macro column as a whole. The next step is sort of the crucial thing that distinguishes my work, I think, from what's there, is that I modulate the I/O functions of the field of neurons according to that rubric there, that as G goes to 1, in other words, as the system's looking at a completely familiar input, the more it's looking at a completely familiar input, I want to ramp the I/O functions up to a very expansive sigmoid, or any kind of nonlinearity, but expansive nonlinearity. On the other hand, when the model is seeing something completely novel, as G goes to 0, I ramp that down to a maximally compressive a constant function. And then I push the V's, the normalized summations, through the units again, and through the modulated I/O function, and yielding a relative probability vector psi in each mini column. And then those are normalized to rows in each mini column, just a full probability measure. And then you just make a soft match. You just pick from the distributions. So that's how the system works. And So you iterate over the weights when you're summing the inputs, and then you iterate a couple times over the units when you're doing some of these other operations, but the dominant term in the complexity would be iterations over the weights. Okay, so this is just a picture of the algorithm storing its first spatial input, that set of five active features down at the bottom. So on step 1, I compute the small lowercase u's there, or the model computes lowercase u's. Oh, all the weights start at 0. So all the U summations are 0 in this case. Therefore, when they're normalized, they're 0. And therefore, all the maximums are 0. And so when I compute G, that's 0. And the I/O function is going to become a constant function up there on the right in step 5. Then I push the V's through the neurons again and get the psi and rho measures, which in this case are the uniform probability distribution. So I make a random choice of units at L1. So that's the code that's going to be assigned to that input. And then I do Hebbian learning between all the active inputs, between the two layers. So compare that to if I present the same pattern again immediately, well, not immediately, but if I present the same pattern again, like I do here, the only difference is that the units that were assigned as the code in the last step now will have summations of 5 in this case, and therefore when normalized, let's assume all the patterns have exactly 5 active units, so I can normalize by 5. That comes into V's of 1, which leads to G of 1, and a maximally expansive nonlinearity. So I modulate the I/O function, I pass the V's through, and you get extremely peaked distributions, row distributions from which you make your choices. And so with very high probability, depending on how the parameters you have on all these steps, you will pick the same code again. So that's how the algorithm works in the spatial case for storage and retrieval. And this slide just shows the point that if I now, so the top panel is just a reduced version of what you just saw. The next panel, I'm presenting a pattern that's slightly different. It's got 4 out of 5 features in common. And if you follow through I'm not going to belabor it, but it leads to lower V's, lower G, a slightly less expansive nonlinearity, and those ultimate row distributions are going to be such that on average, you'll make a few more errors across the mini columns. And so if I now have an input with 40% overlap or 20%, or this is 0% overlap, you can see the I/O function collapsing on the right. And so what this gives you is similar inputs lead to similar codes. And depending on the parameters, you can have any kind of schedule of that mapping. So this is some actual recent data on one of my projects. This is just a little movie in a 12 by 12 pixel patch taken from, carved out one of those H2 videos. So it's a 40 frame feature, 40 frame little video snippet, looks like that. Those are the 40 frames in sequence, and that's the model that I use to present it to, with 3 internal levels, 1 macro column. I go back and forth between the hexagonal and the rectangular format because I haven't implemented hexagonal grids in my software yet. But in any case, the L1 macro column's got 16 mini columns, each with 16 units, and similarly above. So there's a total of 207,000 binary weights in this. I don't know how much information is present in that 40 frame sequence, but it could be computed pretty easily. And this is not tuned or anything, or optimized in any sense. So the bits per synapse here is going to be low, but the principle is actually more important. So in the next slide, I show. Okay, so sorry about more text on this slide, but this movie here just shows the first 8 frames of the learning trial, and the first 8 frames of the recognition trial. And, sorry, maybe I'll use this thing. So this is just to show that it basically gets it perfectly correct. The sequence of codes that light up in the macro columns at the different levels over time are almost exactly correct. There's a few errors made here and there, and like for instance on the last frame, if you look down on the lower right here, there should be, did it get to it? I don't know why, is that red? Sorry about the size. Well, in the first frame, when it first starts, there's an error right here. But this is an error in 1 mini column, not in the whole code. The code is defined over the macro column. And these are corrected on the next time step in all cases. So this self-corrects through time. Okay, so it's got sort of a built-in fault tolerance. This is my second slide. This is an older sort of image of similar information, and I just wanted to show this so you can see the idea that the bottom, on the next time step, the bottom up, and this can be either during learning or recall. But here you'll see the confluence of the top-down, horizontal, and bottom-up vectors, which then go into that algorithm. And so all the model does is on every time step, in every macro column, at every level, computes that three-way intersection of information. And you could have a fourth vector coming in, or any number of vectors, and reinstates the codes. So that sort of gives you a flavor of how it works. Okay, so I think this is relevant to this audience because these properties here of constant time retrieval and storage and retrieval of nearest neighbors. I haven't actually, I don't believe it's out there. I don't think there's any other algorithm that's published. I know that, INDIC is working on locality-sensitive hashing, but their time complexity isn't actually constant. And then there's the word hashing, semantic hashing, and Hinton's work, but the learning half of that uses all sorts of gradient descent and various algorithms. So I think it's pretty unique on that level, and therefore, probably something we should keep in mind as we build hardware. I did a little preliminary mapping of it onto the Memristor circuit, but I don't have time today to show that stuff. But it works with any. It's a software solution. It's an algorithm solution, or really a representation solution. So it should be compatible with any number of hardwares. Okay, thank you. I don't know if there's time for questions, but move along. Okay. Yeah, sure.
Good morning, everyone. My name is Matthew Pickett from HP Labs, and I would like to thank the organizers for the opportunity to speak today. Today, I will be broadly talking about the convergence to cognitive systems. And specifically what I mean by convergence is attempting to develop a straightforward pathway from the state-of-the-art silicon CMOS-based systems to a future environment where we have state-of-the-art silicon systems in addition to emerging device-based, let's say, Neuro-inspired architectures. And I'd like to try to present a framework for a situation where these two types of systems can play well together and actually feed off of each other in terms of creating an ultimate product where at HP we can actually provide our customers with products and services that enhance their ability to process big data and provide in the end sort of intelligent systems. So I'll start with some context by just briefly going over some of the recent trends in high-performance computing. Then I'll introduce COG, which is our attempt at a massively parallel programming model. Essentially, it's a framework for building models of intelligent systems that you don't actually have to, as the user, manage the massive parallelism of the hardware that's running underneath that. So it is a software solution for essentially building models that map well to massively parallel systems regardless of the underlying device technology. Then I'll change gears a little bit and talk about Memristors as biomimetic nano devices, what they can offer as solid-state analogs of particular types of, let's say, biological devices that work in the brain. Specifically, I'll talk about non-volatile memristors as synapses, which many of you are probably already familiar with, and I'll introduce some newer work that we've done on what we're calling MOT memristors, which actually act as solid-state analogs of ion channels in biology. And then I'll finish with hopefully some provocative outlook for discussion later. So I've found this diagram to be really insightful. It was put together by Winston Saunders at Intel, but it really summarizes well the current state of the art in high-performance computing by plotting just a cluster plot of the top 500 systems as a function of their performance versus their efficiency. And you can see that they get clustered in a relatively predictable manner. The bottom of that triangle is essentially the definition of the top 500. That's the performance cutoff, so that's not exceptionally interesting. What's interesting is the top of that triangle, which is really the power bound. All of the systems that are along the edge of that top boundary are essentially in the 15 to close to 20 megawatt range. And that's really the overall infrastructural bound for a supercomputer today, and probably will be for the foreseeable future. And what's interesting is that in order to go up on that triangle, you have to go to the right on that triangle. So what you see on the right-hand side is really the technological limitations of current state-of-the-art systems. And I believe Winston Saunders calls that the edge of innovation. And it's really where the future of computing needs to be pushed. If you want to increase performance, you have to necessarily increase efficiency to stay within your power budget. So we've really arrived in the age of power-constrained computing. We're well into it. Even over the past 5 years of supercomputers are in that situation. Another interesting thing that you see on this plot, which probably doesn't show up in any other obvious way, which is why one of the reasons I find this plot so insightful, is you can see sort of these discrete jumps in efficiency, which additionally give you discrete jumps in the top of the performance bound. And what that is coming from is optimizations in the underlying technology, not just the device technology from scaling, but also architectural innovations in the overall system. And it turns out that architecture is really what's driving efficiency these days, because the power expenditure overhead is not necessarily in the single transistor itself, the bit computation. It's in distributing those bits to where they need to be, putting them in memory, storing them for later, putting them in storage, storing for well later, and putting them back into that one transistor to compute again. So in order to push that efficiency bound, what needs to be done is minimizing communication distances, developing ways of efficient parallelization, whether that's algorithmically or also importantly in the architecture itself, and also to localize the memory and the storage. Get that memory, get the bits as close to compute as possible. And again, what this shows you is that if we want to achieve exascale, we've got a requirement of at least a factor of 150 improvement in efficiency, just from this power bound alone. So the state of the art in many core architectures, which is really driving efficiency, are these massively parallel multi-core systems. The two probably most prominent examples are Intel's Xeon Phi architecture and NVIDIA's Kepler architecture. And if you just look at, sort of the baseline stats for these, they have about the flops count of your average 2001 top 500 supercomputer. So despite the fact that frequencies saturated around that time, we still have been able to progress by improvements in architecture and scaling to a point where we can condense a supercomputer of the time down to a single brick. And this is certainly a trend that will continue over the next decade. I mean, of course, there are limitations, physical limitations to this trend, but it's a fast-moving train, and we can still exploit improvements in architecture in order to move ourselves toward a future where we can implement, let's say, algorithms that reflect biology on traditional CMOS. That said, there are some architectures in the pipeline which do some increasingly interesting things more than just cache and compute. They actually incorporate storage, compute, and cache. And this is a medium-term type architecture that's being worked on by one of my colleagues at HP Labs, which is called Nanostore. It's essentially a scheme for taking all of the storage that you typically get in a data center and putting it directly on the core so that all of the communication from storage or memory to core gets eliminated, or at least as much as possible. And each of one of these augmented cores sits on top of a network fabric. And the medium-term vision for this sort of thing is to get into a situation where we use 3 different physical phenomena for different types of operations in electronics. First, we still use electrons to compute. Second, we use photons to communicate. Photons do not suffer from the charge-discharge problem of communicating with an electromagnetic or with an electron signal. So it's much more power-friendly. There are clearly some challenges with communicating using silicon photonics, but they're not insurmountable, and it is the future. And third, we'll use ions to remember, specifically ions in Memristors, which are CMOS-compatible storage devices that can be stacked on top of computing cores. In the longer-term outlook, we have a vision for what we're calling a converged architecture, where you have a many-core system, and each core potentially serves a more specialized purpose than a many-core system today, but not necessarily so specialized that the entire chip is only good for a very limited type of computation. We're talking a lot now about getting rid of the program. The program is the problem. Well, the program is really what enables computing technology to be so incredible. You can decouple the hardware from its application. And that's why you can actually get the economic benefits of creating a general purpose system. In this vision, it's sort of a convergence of the two. You have special purpose cores that can, for example, be designed as a collection of, let's say, emerging devices which potentially execute very quickly and efficiently a particle filter calculation, for example. But that's not the only thing that you're going to be doing in your system. And you need some other way of managing how that particle filter interacts with some other pre-processing in the system. And actually shipping those bits back and forth between the two is a significant portion of your power budget, and having that on the same chip is potentially critical. So we're not necessarily proposing a brain simulator chip. We're proposing a tool which will which we say is based on disciplinary convergence. So with that, I'll introduce COG, which is this massively parallel programming model. What is it, roughly how it works, and a simple example. So the problem here is one of practicality. When you have a massively parallel system, potentially with heterogeneous cores, how do you program that? How do you program that from a system standpoint where you have, an application expert in cognitive computing that shouldn't learn how to program a massively parallel system? It's an incredibly difficult enterprise to program a massively parallel system, and generally speaking, having people with specialized and distinct domains of expertise is what you want. Additionally, what happens to all of the software that you have when, let's say, a neuromorphic hardware becomes available? Are you able to remap that C code onto that? Do you need to completely reinvent how your system is working? What's going to happen then? And additionally, how do you design, test, and validate neuromorphic hardware? Before anybody is going to invest tens of millions of dollars in developing a chip, whether that's a government organization or a private organization, it's not important. You need to present some sort of compelling value case there with simulation. But if you're trying to make a device that does intractable calculation, how do you validate it? Do you just try to build it from ground up and bootstrap it? I don't think so. I think you need to be able to simulate something like that on conventional hardware first. And once that hardware is available, you need to be able to use a similar programming model to actually exploit that new hardware. So the solution here is to attempt to decouple model design from the nuts and bolts of parallelism as much as possible. I mean, it's essentially attempting the same thing that object-oriented program did to abstract away the complications of assembly language. You need a programmable programming model, but the existing ones don't work well for massively parallel hardware. It's extremely difficult to get them to play together well. So the constraints on this model need to be, it's abstract enough to represent an arbitrary problem of interest. It takes several weeks to learn for an experienced model builder, and it's high level enough to actually use on a day-to-day basis and be productive in it. And critically, it also needs to map well to arbitrary massively parallel hardware that's available today and in the future. So the programming model that we're working on right now is deceptively simple. It's based off of two constructs, a tensor field and an operator. Now, a tensor field is a collection of data that's constructed by the user in a way that represents something important for their model. And an operator is just a description of how that field evolves over time based off of its current state and the current state of some other fields in the system. Essentially, it's a state machine model. It's sort of like designing hardware, but it's constrained in such a way that it exploits massive parallelism in a hardware system. And feedback pathways, whether through other fields or direct feedback onto the same field, provide the dynamics necessary for learning, contextual inference, and the ability to execute difference equations. So it is a very powerful computational model. And again, because of the constraints of the model, although you may be uncomfortable with it when you're first using it, you're able to create a compiler which optimally compiles this model onto a broad range of massively parallel systems. So the current status of the programming model is that it's up and running on a system with tens of thousands of cores. And the models can scale pretty elegantly and can be built by somebody with essentially zero knowledge of how parallel systems work. You can build an operator and field model which represents the problem of interest. The compiler will optimally convert that model from this operator field type thing into code that operates on GPUs. And again, the long-term vision is to create a system that runs well on future architectures, whether they're medium-term or long-term. So a simple example of using COG is to look at what I call the hello world of pattern recognition. Look at handwritten digit recognition from the MNIST data set using perceptron, which is one of the first pattern recognition algorithms. It's relatively simple to understand, very simple to program. You can do this by introducing 4 fields. The first field is the input, the digit, the little image slice that you're inputting. The second field is the weights, essentially what's equivalent to the model itself. The third is the prediction or the output of the system, which is dependent on the current input digit and the current state of the model. And the last is when you're training the system, the label that's associated with the particular input. And using the word tensor field to describe the data here is perhaps a little bit too general. What we mean by tensor field here is essentially a 2D array of scalars for the digit and an array of 2D arrays of scalars for the set of weights which represent the different classes from 0 to 9. And you can see that learning is introduced here by having a feedback pathway from the prediction back to the weights, and the prediction is dependent on the weights. So essentially, it's a robust enough model to implement a wide variety of learning algorithms, but in this case, it's just a very simple example. So I'll just show the evolution of the weights field during one epoch of training on the MNIST data set, this particular model. You just start out with randomly initialized weights. Basically, it's a good way to eliminate some sort of built-in bias to the system. After a few cycles, you begin to see the projection of specific examples onto the different weight fields. And essentially what it's doing is it's telling the system what a 0 looks like and what a 0 doesn't look like. As you show more and more examples, the model tends to generalize. And after one full epoch, you have a fully generalized picture. Now, MNIST is not a linearly separable data set, so this isn't by any means the most accurate way of doing it, but it provides a good example of what COG is useful for. We've implemented a large number of different learning laws in COG, and it maps really well, it parallelizes really well, again, without any real understanding of the model builder, how the internals work. With that, let me change gears and discuss some of our recent work on Memristors, which, in a longer-term vision will serve as, again, biomimetic nanodevices for emerging architectures. But in shorter term, will actually act as non-volatile memory for classical systems. So for those of you who are not familiar with what a memristor is, it's essentially a 2-terminal electronic device that exhibits hysteresis when you apply a voltage across the device. And the most common, or probably the most recognizable type of memristor is the non-volatile memristor, which exhibits non-volatile hysteresis. You sweep the voltage up, it turns from the conductive state to the non-conductive state. You sweep it back down to 0, it remembers that it's in that non-conductive state. In order to put it back into the conductive state, you have to apply the opposite polarity to push it back into the conductive state. This type of behavior has been known for close to 50 years now, but it's finally getting to a point where it's becoming commercially viable. The Mott memristor is a different type of beast. It exhibits a volatile type of hysteresis. And I'll explain in a little while why we call it a Mott memristor these days. But essentially, as you sweep the voltage up, it will change conductance and exhibit a bistability. But as you remove that voltage, the conductance will return to some ground state. And this type of memristor is actually useful for different types of operations than the non-volatile memristor is useful for. And again, both of these types of phenomena have been known for a long time. The types of applications that we're interested in for non-volatile memristors are, most obviously as a non-volatile memory based off of arrays of binary on-off type memory devices. And the reason that this is, one of the reasons that this is interesting is that the process is CMOS compatible. So you can actually build this type of memory on top of a traditional CMOS core. The other application that is probably most interesting to the folks in this room is using a memristor as a solid state analog for a synapse. So you can actually push the state of a memristor away from the binary regime. You can apply pulses or spikes, if you will, which tunes the memristor from an analog standpoint. And a number of people have been showing some results which are interesting from mapping biological learning algorithms directly to the hardware. In this case, the memristor weight. Some other interesting types of applications that can be performed with memristors include stateful logic and reconfigurable architectures, but I won't address those at all here. The most recent results that we've had from a commercialization standpoint, basing this off of our collaboration with SK Hynix, are 50 nanometer process, CMOS compatible test chip that has 2 megabit arrays on it. And so this is a very important step towards commercialization, and essentially the first products will be along the lines of conventional storage products, flash replacement type products, rather than neuromorphic products. But the engineering and expertise that's gained through this exercise will be directly applicable to using memristors in, let's say, future architectures, biomimetic types of applications. So I mentioned before a Mott memristor. What is a Mott memristor? Well, it turns out that if you take particularly an oxide that exhibits an insulator to metal transition as a function of temperature, which is personified by this plot here, put 2 electrodes on it and drive a current through it, you will frequently see a phenomenon that looks something like this. It's been characterized as a negative differential resistance behavior. It's also called threshold switching, but essentially you have a bistable region where for a given voltage you can either be in this high resistance state or this low resistance state. And phenomenologically what you see is that in a lateral device, as you ramp up the current, you see these filaments start to form. And what's happening here is that as you ramp up the current, there is some Joule heating that occurs here. And if you heat locally to a point that surpasses this temperature transition, you get this almost discrete drop in resistivity. And when that happens, you create this biphasic region where you have a filament which bridges the electrodes, and the surrounding insulator, this filament being composed of the metallic phase that's at a higher temperature. As you increase the current through the device, that filament actually grows because there's more heat, and the equilibrium point between insulator and metal grows or moves laterally. And you can see that directly in temperature maps of devices like this. This is taken by infrared imaging, which is calibrated to output the temperature spatially. And you can see that right before that switching threshold occurs, you have a temperature distribution which is more uniform and is just below that transition temperature. But as you drive more current through it, you get this localized columnar hotspot, which is above that transition temperature. So you can see directly these metallic regions in the temperature signature. So that's physically what's going on here. You might ask, how would you propose using a temperature-driven effect for computation? That sounds sort of against the direction that we want to go. But it turns out this is a 10 micron scale device which is used for research purposes, just actually spatially resolving a thermal filament. But if you make a nanoscale device, you can actually see that by virtue of that nanoscale volume, the amount of energy that you need to put in the system to cause that transition it turns out to be quite small. And the amount of time it takes to do the heating actually turns out to be quite small as well. In some of our first devices based off of this phenomenon, we're seeing switching times on the order of 1 nanosecond and switching energies on the order of about 100 femtojoules. So it's in the right range to be considered a plausible candidate for some interesting switching behavior. Now, that begs the question, what can we possibly do with this bistable type of phenomenon? Well, we've been thinking about it for quite some time and came up with a scheme where we use this type of device as a solid-state analog for the ion channels in a biological system. And this approach is inspired by a concept that was, again, put forward many years ago by Crane at Stanford, a concept of the Neuristor, which is essentially a solid-state device which mimics the spiking behavior of a biological neuron. Now, take this with a grain of salt, because what we're not trying to do here is to emulate exactly in a mathematically precise way. We're trying to factor out what we hope to be the most important aspects, which essentially are threshold-based spiking and refractory period for elementary computation using Mott Memristors. You can see, sure.
So earlier you were referring to ion channels,
Mm-hmm.
and I was looking at your first pictures of graphs about Mott Memristors, and it looked like there was a voltage-dependent threshold that was absolutely key. In fact, what I took away from looking at your initial pictures was sodium channel, voltage-dependent sodium channel. And is that where you're coming from on this?
Yeah, that's exactly where I'm coming from. Basically, let me go back to this slide here at least. This switching occurs here. It's driven in current bias mode, but you can drive it in voltage bias mode, where the switching will occur vertically rather than horizontally. And the goal there is to roughly emulate an ion channel.
Thank you.
Mm-hmm. Yep.
Did you put the switching energy in terms of KT?
Not off the top of my head. Let's talk about that afterwards. I haven't done that calculation. So basically, this is a schematic for using two Mott Memristors, which are oppositely biased in a similar way to the sodium and potassium channels of the Hodgkin-Huxley circuit, where The channels themselves are represented here by a variable conductance. These, the Mott memristors exhibit this variable voltage dependent conductance. The state variables of this system are governed by the thermal capacitance of the device, which regulates how quickly the switching can happen, in addition to the charge on the capacitors. So the capacitor, the capacitors in these channel analogs and the memristors both exhibit some state variable that controls the dynamics of spiking here. And this is a simulation of that circuit, which exhibits the threshold-based spiking behavior. If you input a super threshold input to that circuit, you exhibit a super threshold output or a voltage spike. There's actually power gain in this situation. The amplitude of the output spike is greater than the amplitude of the input spike. If you input a sub-threshold input, this Neuristor circuit will actually attenuate that, and it won't be transmitted to the output. So it essentially behaves similar to a threshold spiking device. The details of the state variables throughout the switching process are probably beyond the scope of the talk, but we can discuss those if you're interested. So we've actually built one of these with discrete components that are manually connected in a probe station. So it's not at a scale of an integrated circuit at this point. But you can see that the experimental behavior is quite close to the simulated behavior for the circuit. And depending on how you tune the characteristic capacitances of those channels, you can actually tune to some degree the spiking behavior. You can change the inner spike interval, the spike width, and how many spikes occur per activation event. And again, please take this loosely, but it's beginning to look, roughly speaking, like spiking behavior in biology under constant current injection, which is the situation that's experimentally performed here. So taking that one step further, what can you do with a Neuristor? Well, it turns out that there has been a scheme for performing Boolean logic with Neuristers floating around for also many years now, but hasn't really been implemented in any way that I can tell. You can use the spike timing and the spike amplitude to actually represent logical operations. You can see plots of, in this case, a multi-input AND gate and a single input NOT gate, where if you input only one or two spikes, you don't get an output. You need all three spikes to actually get an output. You can modulate these resistances to get a weighted threshold, for example. Yeah.
So could you implement a spike timing dependent plasticity rule?
I don't see why not. The input timing is critical here too, which goes along that point. This is a plot of the output amplitude as a function of the let's call it jitter, how far apart the spikes arrive. And it turns out that spikes, if there's one spike that's late, one spike can be a little bit late or a little bit early and it'll still fire, but they need to be relatively synchronous. And the same goes for the NOT gate. And it turns out that you can do a lot of conventional Boolean type operations with this type of circuit, which will be published in an upcoming paper. Sort of for fun, what we did was we extended this to build a proof of principle of universal computation with Neuristers. So essentially we implemented a one-dimensional cellular automaton, Rule 137, which is essentially the simplest system that has been proven to exhibit universal computation, implemented in simulation with Neuristers, and the behavior in terms of output spikes at a given cell as a function of time behave exactly as the algorithmic rule of Rule 137 is expected to behave. So essentially what this does is it just demonstrates a proof of principle of the computational power of this type of device, which is based off of phase transitions. So with that, I'd just like to finish with hopefully a provocative outlook, which will introduce some discussion probably later in the day in the discussion section or over lunch. What does the future look like in terms of, a specific purpose or even a general purpose cognitive processing unit? Does this convergence model make sense? Is this framework of computation useful for the models that you're interested in, especially the biologically oriented people in the room? I'm a device guy, so my range of expertise pretty much ends at a relatively low level. But does this mesh with where you're going? Could you use this type of system in your research or in an eventual product? So with that, I'd like to thank you for your time. Yes?
Well, I'm a neurocircuitry guy, and I can tell you that at first blush, this is one of the most provocative advances in terms of conceptualizing the hardware towards neural computation that I've seen in the years that I've been going to conferences in this field. I have more questions later for discussion, but just right now I want to ask you, how close are you to putting the memory local to the routing? You correctly pointed out that that's a big part of the load, is going off and on away from the compute to get to the memory for routing neural circuitries. You said that new architecture that you were having them together close by in proximity in space. Is that something you're doing with Memristors? Are you there yet? Is that something you want to do in the future?
So the question is, how close are we to putting, let me paraphrase, memory close to computing, let's say. I'm bound by not stating any forward-looking timeframes. So I can't give you anything quantitative. But unfortunately, I'll have to reiterate that, our published future architectures have that as a central point. So it's certainly critical to push the edge of that efficiency bar further. The question here?
So you've identified a way of using Memristors to implement one of the key functions of neurons, which is to spike, to act as a threshold device. But really the only other key function of neurons that you need to do computation of this sort is memory. And the memory in neurons is in the form of synaptic strings. It's very clear that Memristors can also function as synapses in which the modulation of synaptic strength forms a memory. So have you pushed along that direction at all?
Again, the question is, have we examined Memristor for synapse in addition to neuron? I didn't cover that as much in this talk because that we have, but that's some older work, and I wanted to show some newer work on the spiking stuff. But I certainly think that that's a critical component of looking at a future emerging device-based architecture, looking at Memristors as synapse analogs and as ion channel analogs for generating spikes. But using two different physical phenomena for doing both of those things, but using a similar conceptually dynamical device, even though they exhibit different physical phenomena. Question here.
Has your group published any spice models?
I've published a number of SPICE models, and I can point you to them if you like. Yes.
You listed the Memristor as a volatile Memristor. And when does it lose its state?
It's a good question. The question is, the Mott Memristor is a volatile device. Let's say, how quickly does it lose its state when you remove voltage? Well, critically, there's a continuity constraint, which is in the embodied heat in the device. So it takes a finite amount of time to pump that heat in and to pump it out for the off switching. And those results are shown here for a nano device. So when you're actually driving the switching, it can take about, in this case, about 1 nanosecond. And it will forget state. If you remove all of that power, it will forget state within a few nanoseconds. So it's a relatively fast process. But it turns out that the fact that it's a dynamical device and has this continuity constraint is important for understanding, designing, and using a spiking device like a Neuristor.
Does it look as if the process of building these is compatible with putting it on a chip with other types of Memristors?
The process is almost identical. It's just a different material between a Mott Memristor and a non-volatile Memristor.
This should probably save you a lot of power. Do you have any estimates of what that power consumption would be if you did build a whole system with these types of devices?
No, and the reason is because a legitimate power estimate necessarily now incorporates the overall architecture, because communication is key and actually becomes a power bottleneck. And until that happens, the number that I give you off the top of my head is probably many orders of magnitude off. So it's not worth even giving you one. One more question.
What's the duration of a spike?
The duration of the spike is controlled by the magnitude of the capacitance associated with that channel. Ideally, we would like that duration to be as fast as possible because it enables us to use a smaller capacitor. If we want to go to biological speeds, we're going to be using huge capacitors, and it probably won't be practical from a density standpoint.